Shear and extensional flow. Shear viscosity measurement. As shown in the figure on the top right, the shear stress is equal to shear viscosity multiplied by shear rate. The shear viscosity can be measured by either a strain control or stretch controlled rheometer. For non-Newtonian fluid and the thermal size, the viscosity depends on shear rate, time, cure, and the temperature. Extensional viscosity measurement, as shown in the bottom right figure. Hanke strain and the strain rate can be expressed by the following two equations. The extensional stress is equal to extensional viscosity multiplied by extension rate. Shear viscosity measurement method, cone and plate. In this setup, gap is fixed. Viscosity related to torque, radius of the cone, and the shear rate. In parallel plate measurement, the gap can be changed. Viscosity is related to torque, radius of the disc, the shear rate. T is torque, R the radius of cone or plate, gamma dot is the shear rate. Capital rheometer is a pressure driven which can go very high shear rate. Viscosity is related to the radius of orifice, the driven pressure, the volumetric flow rate of the sample, and the length of the orifice. Dynamic shear viscosity measurement. And this one just show in the dynamic measurement, the test fixture is oscillating with time. So all the input output parameters have either psi or cosine function in there. So tau is a dynamic shear stress, and G is dynamic shear modulus. G star complex shear modulus is equal to G prime plus I G double prime. The eta dot complex viscosity equal to the real viscosity part minus I imaginary viscosity part. Viscoelastic material property, dynamic shear modulus, and viscosity. So in the dynamic test, we can get both dynamic viscosity and dynamic shear modulus. The output of this dynamic test has two parts, in phase G prime and out of phase G double prime. The G star is equal to G prime plus I G double prime. Dynamic complex viscosity eta star is equal to G star over I omega, the angular velocity. The figure on the right shows a dynamic test for PDMS, the silicon putty. PDMS is a liquid lag at a low frequency or long time, which has a low modulus, and a solid lag at high frequency or short time, at where it has high modulus. Viscosity as a function of time for several liquid at room temperature. So this figure shows the time-dependent viscosity for several material. As shown in this figure, all this material is viscosity very consistent, doesn't change much with time. Complex viscosity as a function of temperature for curable liquid. So this one figure shows the complex viscosity as a function of temperature. As you can see, first, the viscosity decrease with increased temperature. After reach 80 and above, the viscosity has dramatically increased due to the curing of the material. Complex viscosity as a function of time for curable liquid at different isothermal temperatures. So this figure shows complex viscosity versus time at a different isothermal temperature. At a lower isothermal temperature, the viscosity increase slower. At a high isothermal temperature, the viscosity increase faster. Complex viscosity as a function of time for curable liquid at a temporary ramp rate. So this is a complex viscosity versus time. So this figure shows the viscosity increase with time at 234 degree per minute ramping rate. So you can see for high ramping rate, the viscosity decrease fast at the beginning, but after 2000 seconds, it start to cure fast compared with 2 and 3 degree minute ramping rate is cure first. Extensional viscosity measurement. A capillary breakup extensional rheometer can be used for low viscosity material. The material in between two plates is stretched rapidly and the diameter change with time is measured by either a laser micrometer or a camera. Break time and extensional viscosity can be obtained for the test. Many processes can be related to extensional flow. So the bottom figure on the left shows the diameter versus time, and the bottom right is show the extensional viscosity versus extension rate.